Hello, my name is Barry and I'm a PhD student at Technion in Haifa in Vincent Tishak's group. I'm here to talk to you today about observer-related terms in galaxy number counts. This talk is based on two papers, one by Vincent Tishak, myself and Robert Fleischke, that you can see on the archive, and one by myself, Vincent Tishak, Fabian Schmidt and Dongui Zheng, that you will hopefully be able to see on the archive in the next couple of weeks. Because we haven't published the second paper, I'm mostly going to talk about results in the first paper and only mention briefly some results in the second one. But I'll give you a promo on that paper so that when it comes out you could see more details in it. Right, so let me start by describing our universe. So the universe is described by perturbed FLRW metric. The background is homogeneous and isotropic, but perturbations make it not exactly so. So if, for example, one observes a galaxy at this position x, or the galaxy's actual position is x, then the observed position would not generally be the same. It will be some other value x tilde that is related to x through the cosmological perturbations. And the reason is that the light from that galaxy to us does not travel in straight lines, and also is redshifted or blue shifted by gravity, and that implies that the inferred FLRW position of the galaxy is not equal to the actual position in general. So there are perturbations, and so the observed distribution of galaxies is not the same as the actual one, and there are certain so-called projection effects or relativistic projection effects that influence it. And the goal is to calculate the observed galaxy distribution and take into account all the relativistic corrections to a given ordering perturbation theory and relate that to the underlying dark matter distribution. And this will include lots of terms, complicated integrals and so on. And let me just mention that because it's an observed galaxy distribution, it is obviously gauge invariant, and it is helpful if one had decomposition into gauge invariant, simple gauge invariant terms that one could use to compute this value of delta. Right, so in actual redshift survey, one looks at the sky and maps all the galaxies, and then to each and then one divides the sky into angle bins and redshift bins. So for example, this bin contains a few galaxies. One counts as how many galaxies there are in this blue square, and then one adds all of them up, assigns a direction n hat to the square and the redshift, and then a division of the number of galaxies by the redshift bin and solid angle occupied by them gives the observed number of galaxies in this redshift bin and in this direction n hat. Now one does that for all for the entire survey, and then one obtains an observed galaxy number count as a function of redshift and as a function of direction on the sky. Now this observed galaxy number count is not equal, as I said before, to the actual distribution of galaxies, and there are a lot of terms in the expression for it. You can see papers by Yu et al., Bonvin and Dura, Chano and Lewis, for example, that calculate it, include relativistic projection effects. Now let me just mention that delta, so this overdensity number, the number of galaxies minus the average number of galaxies, the mean, um, it depends on the entire line of sight. So if we go back to the figure that shows the relation between the actual position and the inferred position, we could see that the line of sight is curved, and it's curved by matter through all along it. So if there is a galaxy closer to us, it will affect how we see a galaxy further away, and it will enter into delta as well. So delta actually depends on the entire line of sight, including values of physical fields like the gravitational potential, the velocity field at the source's position, and also the observer's position, and also terms that include an integration along the line of sight, like some gravitational redshift, and so on. Right, so it's important to bear in mind that all these terms appear in expressions for delta, because this will be important later. Now, let me show you such an expression for the observed galaxy over density. Now, if you consider some ruler quantities, which will be called C, T, and M. I will just in a second explain what they are. Then you can write delta like so, as I've shown, where this delta OR is the galaxy over density on a fixed observed redshift surface, which is gauge invariant because it is evaluated in a constant observed redshift gauge, and it is what is directly related through the bias expansion to the dark matter over density. Now, this equation relates delta to certain ruler quantities which measure how length and time scales change between the inferred one and between the inferred length or time scale to the intrinsic one for a clock, for example, in a perturbed spacetime. So let me describe T first. So T measures the difference between the scale factor at a fixed proper age and the scale factor at a corresponding fixed observed redshift. Now, in the background spacetime, in FLRW, a certain given proper age in a certain given observed redshift imply that the scale factor is equal. But in a perturbed spacetime, this might not necessarily be so, and so the difference between them is measured by T. And C and M measure the change of size of a ruler, the inferred size of a ruler. So for example, imagine that one places a ruler from x to x prime, whose sizes are naught. Well, the observer will see a different size. The observer will see an r tilde, and this change occurs both in the longitudinal direction and in a transverse direction. So C measures the change in the longitudinal direction, while M measures this change in the transverse direction. More details about those ruler quantities can be found in a paper by Dongwijung and Fabian Schmidt from 2012 and 2014, and also an explanation for this formula will be found in the forthcoming paper by us. Let me just say that as they measure physical observables, C, T, and M are gauge invariant quantities, and therefore this equation expresses gauge invariant decomposition of delta into observable gauge invariant quantities, each of which has a clear physical meaning. And it's also much simpler than the full expression for delta. Right, but as I said, C, M, and T, they all involve terms that depend both on the observer and the line of sight and on the source's position. Right, and so what do we do with this equation? Well, we can calculate correlation functions. Now, because we've included all the relativistic corrections in this equation, we should be able to compute the power spectrum and more usefully the angular power spectrum, which is what I'm going to show you now. So you define the angular power spectrum in the usual way, and then you express it as an integral over wave vectors, and this plot shows the integrand of this integral as a function of the wave vector, okay, for equal values of k and for some values of redshifts which determine chi. Now, as you can see, for example, we can compute that for the monopole because we have included all the observer-related terms, and the monopole looks somewhat like this. Well, it depends on the redshift, but it starts at some finite value, it goes down, and then it oscillates. So that's the integrand of C0. This graph does not include the matter power spectrum. So take the value, whatever you get from this graph, then you might multiply by k squared times the matter power spectrum, you integrate, and then you get the correlation function, the angular correlation function. Okay, so this is, and of course this can be done for any value of L, for any multiple. Okay, so let's move on and talk about the effect of placing an observer in more detail. So as I mentioned, because delta does not depend only on the source, it also depends on the observer and on your line of sight. It refers to a specific location in space, and therefore it is not a homogeneous random field, but rather an inhomogeneous one. While one could say that it is not important where we put the observer, this is true, but still we have to put an observer somewhere, and putting an observer somewhere breaks this symmetry of homogeneity spontaneously, right? So having an observer is an instance of spontaneous symmetry breaking. And because the observed values are not homogeneous, some care must be taken when computing the statistics. So, for example, as we will see, the correlation function does not depend only on the distance between 2 points. It also depends on the points themselves. And this dependence is not surprising because it can also depend on the relation between x, for example, point x and point y, and x equals 0, which is where we put the observer. So it depends also on x and y alone, and not only on the distance between x and y. And because the existence of an observer, one must impose some constraints. And the main part of the talk, or the next part of the talk, will explore why one should impose those constraints and how one could deal with them. Right, so going back to the redshift survey, we have an observer now at the origin. The observer measures the galaxy distribution, and let us assume that inside the expression for the galaxy over density there is some random field, some cosmological random field f, for example the potential, that enters into the expression. And for simplicity, I'm going to assume that f itself is what O measures, or rather that f is enters in a very simple way. But it is crucial that f at the observer position, the observer's position, also enters this formula. So the observer measures some random realization of f, chosen from some ensemble. But this random realization cannot be any random realization, because it has to satisfy a constraint that f at the origin equal to some number, some value, fo. And the reason is very simple. So if you think of f as specifying the number of galaxies, then obviously one cannot expect to measure a random realization where at x equals 0 there is no galaxy, because an observer has to be in a galaxy in order to observe from f equals 0. So f at other values, so for example f at this value, somewhere, I don't know, redshift 0.1 for example, is correlated with its value at f equals 0. And therefore the realizations in which f at 0 is not equal to fo have to have 0 probability and not a finite probability. And that implies that f is not just any random field, it is a constrained random field. And the constraint is that it satisfies this equation at the origin. Okay, so again, let me repeat that. So the observer measures redshifts and directions from galaxies, and the observer also can measure some local properties. So if the observer can measure f at x equals 0. The only realizations which O will measure are those which agree with the specific value fo at the observer, for otherwise they should have 0 probability. And so the statistics of this random field is such that it always has the value f0 at x equals 0, and therefore there are some constraints. Okay, and this is true always when the observed random field depends explicitly on observer terms, such as for example in the case of delta, the observer's velocity or the local density at the observer's position. Okay, so treating fo, the value of f at the observer, as a random variable misses the fact that we fix it by placing an observer there. Let me mention a paper by Mitsu et al. Which takes a different viewpoint on this issue. And let me mention that in the end we will see that this change in statistics changes correlation functions in such a way that is always that the difference between using constrained statistics and unconstrained statistics is always smaller than cosmic variance. So in the end we will see that practically it is not such big difference, but conceptually it is still important. Now I will also mention that as constraints arise from correlations between observed quantities and observed quantities at the observer's position, they must be imposed by gauge-invariant in a gauge-invariant manner. But for the exposition of this idea, we will simply assume that f itself is a measurable random field and that it is directly measurable, so that we won't be troubled by the question of gauge invariance. Okay, so I'll repeat that the observed value of a certain cosmologically interesting quantity depends explicitly on f naught on fo, and therefore it is correlated with it, and therefore one has to modify the statistics such that this correlation is taken into account. How does one do it in practice? So this has been known for quite a lot of time, since the work of Hoffman, Rybak, and for example also van der Weigert and Urchinger, which studied constraint statistics. We will be interested mostly in the two-point correlation function, and this two-point correlation function can be computed as follows. So you take one wave vector k, another wave vector q, and the expectation value of this product constrained such that f at x equals 0 is equal to 0. So we took f o equals to 0 for simplicity, is given by this equation. Now the first term in this equation is the usual unconstrained term, while the second one is a correction. So you can see that as before we had the correlation function in real space that didn't depend only on the difference between the distance between the 2 points. Here we have a correlation function in Fourier space that is non-zero also for k not equal to q. So delta here is a Dirac delta function, so this entire thing is proportional to the observation volume. And the second term is the power spectrum at q, the unconstrained power spectrum of f, of the random field f at q, divided by the variance of the random field, which is not a function of q or k because it's a variance of the unconstrained field. So these quantities on the right hand side, p and sigma, pertain to the unconstrained field before we placed an observer. Okay, and this quantity on the left is the correction. It describes the correlation function when an observer is placed at x equals 0. And I will also mention that for k equals q, and when we take the limit k goes to 0, this correlation function actually goes to 0. So this regularizes it automatically, which is quite a nice property. But it is important to bear in mind that this arises at k goes to 0, and in practice there's a finite observation volume, and so there's a finite there's a finite number, or sorry, there's a discrete number of values that k can take. Okay, now let's see what happens in practice when we calculate this correlation function. So if we choose a finite volume and we take finite values of k, so finite meaning non-zero, then we can calculate this equation. We can for a choice of a random field, and calculate the power spectrum of the unconstrained field and compare. And this is what we did for a random field f given by the Bardeen potential minus the value of this potential at the observer, and this is the same as choosing the constraint f o equals 0. So it's the same as choosing the potential at the observer to be 0. Now on the x-axis you can see the wave vector, and on the y-axis you see the observed expected value of the power spectrum. So you can see the left hand side of this equation on the y-axis. Now we took an unconstrained power spectrum, which was simply a power law, and we took different values of observation volume, and we computed this expression for the constrained and the unconstrained statistics. Now in black you can see the constrained statistics that go down to 0, and in red you can see the unconstrained power spectrum, which is simply a power law. In gray you can see cosmic variance, right? And what happens is that, let me just mention that the y-axis is of course the expectation value of an estimator for the power spectrum. Yeah. So what happens is that these the difference between the constrained statistics and the unconstrained statistics is always smaller than cosmic variance for every value of k which is bigger than the minimum value of k, which is dictated by the observation volume. So it goes like v to the minus 3. Right. So the conclusion is that while conceptually very different, constrained and unconstrained statistics for cosmological observables give the same practical answers, in the sense that the difference between them is always less than cosmic variance. Of course, this can change theoretically when more constraints are added, but this would have to be looked into, of course, on a specific for each specific random field. But we expect that the conclusion to be true for cosmologically viable choices, this conclusion. Right. Let me also mention before finishing what happens when one chooses to decompose the random field into spherical harmonics instead of using a Cartesian Fourier transform. So what happens is that the entire constraint is absorbed into the monopole, L equals 0. And this is not surprising because the constraint was that the value of f at a point be equal to some number. And higher multipoles measure deviations of the random field. So they measure fluctuations, and the monopole measures the average. So it makes sense that the constraint affects only the monopole. Of course, if you had more constraints such as the velocity of the observer, then there would be higher multipoles, so the dipole would be affected. Okay, but more importantly, the statistics of high multipoles are unconstrained, so that we get precisely the same statistics for high multipoles as the unconstrained statistics, and then this is quite good news because we could use those multipoles to infer interesting physical quantities. Okay, so that's it. Let me summarize. So in this talk we saw that the observed galaxy orbit density depends on the entire line of sight. It can be expressed as a combination of these Ruler quantities, each of which depends on the entire line of sight. Importantly, this observed galaxy orbit density includes terms that are observer related, so values of random fields evaluated at the observer, for example, the value of the potential of the observer. And these terms imply that the statistics of this observed galaxy orbit density is not the statistics of a homogeneous random field, but rather exhibits some broken symmetry. And this symmetry is the symmetry of choosing where to place an observer. Breaking this symmetry implies the existence of constraints, because correlations exist between the values of the random fields at the source, for example, and the random field at the observer. And treating these constraints with care gave us some formulae for the correlation functions. Of course, one could calculate higher order correlation functions if one wanted to. So bispectrum and so on, and higher point functions, so 4-point functions, etc. One can calculate all of them even for a constrained random field, for example, in a path integral formulation. Dealing with these constraints changes those correlation functions relative to the unconstrained ones, but we have seen that the difference between them is always smaller than cosmic variance for a given finite observation volume, so that in practice this um, difference. I mean, this change of statistics does not imply different results than the ones we have, but it is conceptually important. So thank you all very much for listening, and I hope you've enjoyed my talk, and thank you for giving me the chance to speak at this workshop. If you have any questions, I will be very happy to answer them. Thank you very much, and goodbye.